Hyperlinks is an integrated family of products for high-speed system design, automated optimization, and verification. By design, we mean all the planning and analysis you do before layout to define the rules you want to use to place and route the board. By optimization, we mean using automated tools to improve design performance for a metric of interest. You can certainly use an interactive design capture, analyze, review loop to improve your design, but that takes too long. We'll look at how hyperlinks can help you improve the design performance automatically. By verification, we mean post-layout analysis, or what you do once the board is routed, to determine the design is ready to release to fabrication. There are three main design application areas for hyperlinks: DDR interface design and verification, which we're talking about here, serial link design and verification, and general purpose signal and power integrity, which overlap with some of the capabilities we'll discuss here. Hyperlinks products include Hyperlink schematic analysis, which automates parametric checks, eliminating the necessity to manually review complex schematics. Hyperlinks AMS, a powerful circuit simulator for analyzing complex analog and mixed signal designs. Hyperlinks DRC, which provides fast, rules-based design checking of PCB layouts. Hyperlinks DRC can identify layout issues in a fraction of the time that simulation requires. Additionally, screening designs with DRC before investing in detailed modeling and simulation will help speed up your design cycle. Hyperlinks Advanced Solvers, which provide accurate 3D electromagnetic modeling of PCB structures and are seamlessly integrated with Hyperlinks SI and PI to provide complete front-to-back analysis flows. Hyperlinks SI performs signal integrity analysis of DDR interfaces, SerDes-based serial channels, and general-purpose high-speed design. Hyperlinks PI performs DC and AC analysis of PCB power delivery networks, or PDNs. Hyperlinks offers a comprehensive suite of signal and power integrity analysis capabilities to ensure optimal performance of your PCB design. In terms of DDR design and verification, the pre-layout phase is used to experiment with various routing and topology schemes, trace and via design, drive strength and termination schemes, investigate stack-up trade-offs, and run a full interface-level analysis using the DDRX batch wizard. Meanwhile, the Power Distribution Network Editor enables the user to efficiently design and verify power delivery networks, including DC drop analysis, and investigate decoupling strategies. In post-layout, the user can run a full interface-level analysis in the DDRX batch wizard on a completed design to verify all signal integrity and timing requirements are met. Hyperlinks can extract models for all aspects of the routed board automatically and provide a full, comprehensive analysis through the DDRX batch wizard. In cases of additional optimization or experimentation, the user can choose to export the design to pre-layout for further investigation of trade-offs. Additionally, DC voltage drop and decoupling performance can be verified against requirements in post-layout. Hyperlinks is tightly integrated with Siemens' family of PCB design capture and layout tools. Design is an iterative process. Using analysis during the physical design cycle can help you tune and improve the design in real time, rather than waiting until layout is complete when it's too late to make substantial changes. Combining hyperlinks with Siemens design capture and layout can significantly reduce your design cycle and improve your design's performance. In addition to offering superior integration with Siemens PCB tools, Hyperlinks is also the most widely interfaced power and signal integrity tool on the planet. With Hyperlinks, you'll have the widest range of PCB import capabilities available. Successfully analyzing a DDR interface involves knowledge from multiple disciplines including signal integrity, timing analysis, and power integrity, and must satisfy a myriad of design requirements. There are signal quality requirements on individual signals, timing relationships that must be satisfied between groups of signals, and even requirements on the power delivery network used to supply DC power to the controller and DRAM ICs themselves. All these requirements must be met simultaneously and with adequate margin under worst-case conditions for the design to work. We're going to look at how hyperlinks can help you meet all these different verification needs. DDR5 brings new challenges to the simulation world. DDR5 adds increased data rates resulting in tighter margins. To combat the reflected nature of a DDR5 interface, JEDEC specifies the use of equalization in the form of a decision feedback equalizer, or a DFE. The complication to adding equalization to the DDR5 protocol presents problems for the EDA tools regarding accurately using IBIS AMI models in the simulation. IBIS AMI models were designed to be used in SerDes simulations, which are inherently differential systems, not single-ended like the data bus for a DDR5 interface. Additional issues with IBIS AMI are related to the nature of the SerDes clocking structure. In this case, SerDes systems rely on a clock data recovery, or CDR, whereas DDR5 relies on clock forwarding structure. This presents a challenge when trying to incorporate the real behavior of the data strobe and the internal clock tree delay. The single-ended nature of the data bus in DDR5 reveals issues with the assumptions of the drivers being symmetrical or having relatively matched pull-up and pull-down characteristics. This assumption will create rather symmetrical eye diagrams, but unfortunately, it isn't reality when looking at DDR5 drivers. Drivers for DDR5 are not matched and therefore create waveforms with unequal rise and fall transitions, leading to an eye diagram that is also unsymmetrical. To combat this issue, the simulation needs to accurately represent these nonlinearities and compute the resulting waveforms. Hyperlinks introduces a special, custom hybrid flow that accurately captures nonlinearities, resulting in a simulation suitable for final sign-off. With other signal and power integrity flows, expert users have to acquire analysis tools from different companies, then figure out how to put them together to create a flow. Users need to figure out how to pass data between tools, including how that data needs to be named and formatted. It's a lot of work, and the process needs to be requalified whenever any of the analysis tools change, because that might impact the overall process and the quality of the results. With hyperlinks, the different tools are already integrated, with reference flows defined and proven right out of the box. This presentation will discuss how the DDR flow covers the full range of analysis, pre-layout design exploration, and physical layout guideline development, automated design optimization, and full system post-layout verification. Post-route verification can get incredibly complex depending on the level of detail in the system model and the type of analysis performed. Although it's tempting to think that every simulation should be as accurately as humanly possible, that isn't cost-effective in actual practice. The time and effort required to create and analyze a system model increases dramatically as the level of accuracy goes up. That's true with any simulation flow, not just hyperlinks. The post-layout environment is a race against time. The board is laid out, and time is money. So that time available for post-route verification is strictly limited. The ideal verification methodology is one that identifies and resolves as many design problems as possible as quickly as possible, with as little effort and expense as possible. Strictly running just detailed simulations won't accomplish those goals. Hyperlinks uses a methodology called progressive verification, where the analysis starts simply and adds accuracy in controlled stages. The goal is to take the simple problems off the table quickly using a faster and less accurate method of analysis. By the time detailed simulation is deployed, only the toughest and hopefully fewest problems remain. Post-route verification with hyperlinks begins with electrical rule checking, which automates inspection of the design for compliance with best practice design rules. No simulation models are required, and this analysis runs quickly. Best practice rule checking can find design issues in minutes that would take hours or days to find with detailed modeling and simulation. Compliance simulation, or so-called model-free analysis, checks the design based on technology models for device I/O and timing. Vendor-specific simulation models are not required. This method is not as accurate as simulation based on vendor models, but it can always be performed even when vendor simulation models are not available. This issue of vendor model availability is very prevalent in DDR5. Since the technology is still relatively new, many vendors have strict limitations on model availability to use for simulation. Additionally, specific vendors for DDR5 may not have extensive experience creating IBIS AMI models necessary to simulate a system with equalization. Device-specific simulation analyzes the design using vendor-specific component models and device settings. It's the most accurate simulation available and also the most time-consuming. When device-specific analysis is preceded by compliance simulation, the final analysis proceeds faster because post-layout topology extraction and simulation setup have already been completed. As we mentioned, electrical rule checks automate manual inspection, finding problems in seconds or minutes that would take hours or days to find using modeling and simulation. These checks cover a wide variety of power and signal integrity issues. Traces crossing gaps in planes are a good example of problems that can be found quickly. A DRC analysis can process hundreds of signals per second, identifying exactly which signals have problems and where. Finding a trace crossing a split using simulation is problematic. The modeling and simulation are time-consuming, the actual effect on the signal quality may be relatively small, and isolating the exact location of the problem from simulation results can be difficult. Hyperlink's DRC performs design checks in a fraction of the time that it takes to perform those same checks manually, producing detailed reports that show exactly where and how each violation occurred. It also produces reports that can be given to PCB designers to quickly locate and correct each problem. Hyperlinks has an extensive rule library for general SI, PI, safety, and EMI, as well as specific checks for DDR interfaces. Once the design rule check has been completed, we can move on to running preliminary simulations using technology-based or model-free approach. Our first analysis uses technology-based models to look for basic signal quality and skew problems. Model-free analysis can be performed and used to find design issues even when vendor device models aren't available. Both model-free and device-specific simulations perform the same JEDEC-compliant analysis and measurement and yield simulation results in the same report format. This enables an efficient way to compare results and see how different models affect different design margins. Generic IBIS models for all DDR protocols are included with hyperlinks. This enables the user to run simulations even in cases where no vendor models are available. These generic models are more simplistic than a vendor model, but still provide useful simulation results to get an idea how an interface is performing. The included generic DDR5 models also include an AMI model capable of equalization. This model can be set up in a clock-forwarded architecture, is capable of manual or adaptive equalization, and even include jitter parameters. IBIS AMI models are included for address, data strobe, and data signal groups, depending on your specific needs. Additionally, Hyperlinks includes a generic registered clock device model or an RCD for those needing to simulate registered DIMM modules. Device-specific analysis replaces the technology-based models used for model-free analysis with IBIS and IBIS AMI models supplied by the component vendors. This accurately models the behavior of the individual ICs and their packages. Modern DRAM devices and controllers are highly programmable, and some optimize their settings automatically, so it's important to simulate these devices as they will actually operate in the system. Hyperlinks allows users to specify drive restraints and receiver termination settings, specify which timing optimizations the controller can perform, and how devices with built-in equalization capabilities will be programmed. Hyperlinks then uses all those settings when performing simulation. DDR simulation reports for device-specific analysis uses the same format as pre-layout and model-free. This makes it easy to compare different sets of simulation results to see the effect on system margins. Imagine a workflow where you manually pick nets of interest, crop or select a subset of the layout, define ports, perform meshing, and extract a model. This model then needs to be added to a test bench comprised of a driver and receiver models to form a final representation capable of delivering simulation results. This is a daunting task, even when considering only a small sample of nets comprising a DDR5 bus. Which nets do you choose? How do you know you have chosen worst-case examples? Now imagine trying to accomplish this workflow on an entire DDR5 interface, verify complex signal, power integrity requirements, and achieve full timing closure. Additionally, each model needs to be created separately if comparing effects such as with and without crosstalk, changes to the stack-up, etc. The point is, this is time-consuming, error-prone, and impractical for full interface-level analysis. So how would we solve the problem? Hyperlinks performs automatic net interconnect extraction, allowing it to excel in post-layout verification over other EDA tools. The automatic net extraction advantage Hyperlinks offers cannot be understated. When a simulation is initiated, Hyperlinks runs the field solver automatically on the selected net or nets. The geometry from the PCB is interpreted by Hyperlinks and used to build a complex interconnect model including the vias, transmission lines, coupling, loss, etc. This model is automatically built and instantiated into the simulation without any additional interaction from the user. There is no cropping necessary, ports to map, meshing to take place, or additional instantiation of a test bench. This model scales whether we are investigating one net or modeling the entire interface. Furthermore, this capability is fully functional in the DDRX Batch Wizard, greatly simplifying the entire process and enabling a fast and efficient method for analyzing an entire DDR5 interface. Hyperlinks provides consistent analysis flows for both pre-route and post-route verification simulation. You can use the same simulation process that produces the same reports, whether you're performing pre-route design exploration to develop routing guidelines or post-layout verification in preparation for final sign-off. You get the same simulation results presented the same way, so it's easy to compare your pre-layout expectations to actual performance of a fully laid out design. DDR5 analysis can be accomplished with two main wizards. The interactive wizard is designed such that a single net can be analyzed and optimized before committing to analyzing an entire bus or an entire signal group. The interactive wizard includes swept parameter optimization to explore trade-offs in buffer settings, stack-up parameters, routing lengths, crosstalk effects, and even equalization settings, among others. The DDRX Batch Wizard is aimed at providing complete interface-level analysis resulting in all effects suitable for design sign-off. Both the interactive and batch wizards are available in pre- and post-layout so that design decisions can be fully realized and verified through an efficient integrated flow. The DDRX Batch Wizard is an all-encompassing, step-by-step guided utility aimed at greatly simplifying the complications of setting up and analyzing a DDR5 interface. The wizard is protocol-specific and can handle DDR through DDR5 and LPDDR through LPDDR5. The user supplies the necessary input files, configures the interface and signal groups to analyze, and Hyperlinks does the rest. Hyperlinks analyzes DDR interfaces using protocol-specific analysis, computing and reporting design margins in a comprehensive report. The DDRX Batch Wizard is available in either pre- or post-layout, enabling the user to check the quality of the interface early and often throughout the design process. In pre-layout, swept parameter analysis can be used to explore trade-offs in buffer settings, routing, stack-up, equalization parameters, and crosstalk effects, among others. These trade-offs can be analyzed using the DDRX Batch Wizard to quickly and efficiently assess design margins. Hyperlinks uses timing models to calculate margins against the complex timing requirements. JEDEC-based DRAM timing models, along with generic controller models, are supplied with hyperlinks for all protocols. Timing parameters are speed grade dependent and include those necessary to calculate worst-case margins. Since JEDEC does not govern controller requirements, only generic controller models are provided to get the user started. These generic models can be considered model-free in the sense that they represent a starting point for timing closure, especially when no vendor timing data is available. However, Hyperlinks includes a controller timing model wizard, allowing the user to create custom models based on the controller timing data. Modern DDR controllers can perform a myriad of automatic adjustments to optimize timing margins. Controller data outputs can be shifted during write cycles to optimize the DQ to DQS timing. Controller DQ inputs can be shifted with respect to their associated DQS signal, and so on. In fact, modern DDR design has essentially become a skew and crosstalk management problem, with the controller taking care of most timing details during power-up initialization and training. In order to predict voltage and timing margins at the system level, it's important that the analysis tool can emulate the adjustments made by the controller, and Hyperlinks does just that. Hyperlinks predicts the final timing settings used by the controller based on the individual controller's capability, then uses that information to report system design margins. Swept parameter analysis can optimize design parameters across the entire topology, and is best used to explore variations such as trace lengths and geometries, and I/O settings and termination values. Users define variable elements and the parameter values to be evaluated, and Hyperlinks generates all the permutations of design parameters and runs the analysis. DDR analysis produces the same reports as before, so optimized results can be readily compared to the baseline counterparts. We've previously spoken about protocol-specific analysis. It's important when we run simulations to set up our components as they would be set up in an actual system, and measure actual design margin using the same methods that would be used to measure margins in an actual system. In other words, simply running a signal integrity simulation and looking for clean signals isn't enough. We need to model and analyze the design in accordance with the specific DDR5 protocol and requirements involved. Hyperlinks understands and emulates the protocol-specific characteristics of a DDR5 interface. Because JEDEC specification only specifies characteristics for the DRAM components, Hyperlinks uses timing files to capture the device-specific capabilities of different DDR5 controllers. This allows both ends of the interface to be completely simulated, with design operating margins computed accurately. The Hyperlinks DDRX Batch Wizard guides users through the analysis process step by step, simplifying setup and ensuring both analysis consistency and accurate results. We previously mentioned how easy it is to add effects such as crosstalk to the analysis. Hyperlinks has a unique way of adding crosstalk to the simulation, enabling the user to select different coupling methods and evaluate their effects. The user can specify different methods or contributions of coupling to help isolate and understand their effects. Potential aggressors can be found via electrical or geometric thresholds, the latter better matching typical routing rules or vendor routing guidelines. Other coupling methods such as trace-to-trace, trace-to-area fill, coupling due to connectors, packages, and 3D solved areas can be turned on or off in a variety of combinations to better understand their effects. Power-aware effects can also be investigated in Hyperlinks. Power-aware can be broken down into two distinct areas: simultaneous switching noise, or the PDN model, or non-ideal return path effects, or the channel model. Power-aware effects are extracted through a built-in hybrid solver and easily included in a single net simulation or the entire DDR5 interface through the use of the DDRX Batch Wizard. Power effects can be considered another level of progressive verification, enabling the user to increase the accuracy of the simulation as needed. Finally, in regard to progressive verification is the ability for Hyperlinks to enable and disable different effects such as crosstalk and power aware. The user can quickly and efficiently add higher order effects to assess their impacts on design margin and performance. When you simulate an entire DDR5 interface, there's a lot of data to report. Hyperlinks organizes and presents all this data so you can answer the question you care about the most: which signals passed, which signals failed, when, and by how much. Margins are reported by signal groups and transactions. Data read, data write, command address, and clock to strobe transactions are reported independently. Measurements are made based on the JEDEC standard for the DRAM and customized for the controller based on the controller's capabilities. Results are presented in spreadsheets that can be sorted and filtered, so you can quickly find worst and best case conditions, filtering the results as desired. Reports are presented in HTML format with summaries and hyperlinks to detailed data. You can also view critical waveforms and eye diagrams directly from the report. The report can also be exported to PDF format for archival and collaboration purposes. Signal integrity simulation is hard enough to run once, but what if you run the same simulation again? Will you get the same results? Surprisingly, the answer with most other tools and flows is no. Model extraction and simulation setup is mostly manual, and there are enough options and settings that there is a fair chance no two simulations will use the exact same setup or produce identical results. The analysis flow and sometimes the output reporting vary slightly from user to user, even within the same company. Worse yet, what happens if an experienced SI analyst leaves the company? Most of their knowledge and techniques leave with them. More importantly, if you rerun the same simulation 6 months from now, what will happen? Manual flows change over time, and so do the results. If you have a design in production that begins exhibiting problems, will you be able to go back and reproduce the simulation steps you used when designing the system originally? Probably not. Hyperlinks automates the analysis process front to back, so the process is always consistent, the analysis results consistent, and the reporting format the same from user to user. It's easier to trace and compare results because the simulation processes don't change. Hyperlinks saves the options you use to set up the analysis so you can reproduce the run, and the simulation settings and version of Hyperlinks used are documented in the report, adding to the analysis reproducibility and traceability. To summarize, the Hyperlinks DDR5 solution aims to solve the unique challenges of analyzing a DDR5 interface. Successfully analyzing a DDR5 interface involves knowledge from multiple disciplines including signal integrity, timing analysis, and power integrity, and must satisfy a myriad of design requirements. Hyperlinks features the most comprehensive solution, including the most efficient post-layout workflow. Additionally, Hyperlinks tightly integrates the entire workflow with automatic extraction of interconnect models. The DDRX Batch Wizard is an all-encompassing, step-by-step guided utility aimed at greatly simplifying the complications of setting up and analyzing a DDR5 interface. Hyperlinks presents a unique IBIS AMI flow aimed at capturing the singleton nature of DDR5 while maintaining efficient performance. Hyperlinks boasts progressive accuracy, featuring model-free analysis for useful simulation even when vendor models do not exist. Hyperlinks presents results in a comprehensive, efficient manner, making it easy to review results, make design decisions, and assess margins for final sign-off. The Hyperlinks DDR5 solution is an indispensable tool for designing and analyzing a DDR5 design. Hyperlinks workshops get you up and running quickly by documenting complete workflows with detailed step-by-step instructions and videos. Hyperlinks workshops guide you through the process with working examples so that you can hit the ground running on your own design simulations. Hyperlinks workshops can be downloaded from Support Center. You can see a list of different workshops on the right of the screen. This concludes the presentation, and remember, it's easier with Hyperlinks.